Welcome to our presentation, OakInk, a large-scale knowledge repository for understanding hand-object interaction. The presenter's name is Lixin Yang from Shanghai Jiao Tong University. Since the year of 2019, we have witnessed a lot of datasets for hand-object interaction, but they all have one drawback. The existing real-world dataset only contains a small number of objects and hand interactions. The number of objects is less than 50. For more realistic and more diverse interaction in the virtual world, we need a dataset that can expand the diversity from the object's perspective, and an algorithm for automatically transferring the limited hand interactions to the unlimited object instance. What motivates us to build this dataset is that understanding the hand-object interaction should not only consider the pose during interaction, but also the affordance of the object and the human's intent on manipulating the object. For example, if I want to use a knife, I wouldn't grasp the blade. To help the virtual avatars and robots to learn how humans manipulate objects, we need to provide the affordance of the object and to show how human hand would interact with it, based on this affordance. These are the core idea and how we named our paper. The OakInk stands for two intercorrelated database, Oak for object affordance knowledge, and Ink for interaction knowledge. We first collect 1,800 objects of 32 commonly used categories. The source of our objects are fourfold: the YCB object, the contact database, the ShapeNet, and also we brought some objects from the online vendors. The affordance is represented by a set of attributes. Each attribute contains a part segmentation with one or several descriptive phrases to describe the part's functionality. For example, given a camera with 3-part segmentation, we assign the phrase "point to something" to the lens. Through achieving the consensus among 10 volunteers of different backgrounds, we conclude 30 attribute phrases to describe the common affordance of the objects that we collected. These objects plus affordance constitute a knowledge base that we call it Arcbase. Next, based on the Arcbase, we seek to provide the human experience to interact or manipulate the object, which is the main body of the Inkbase. We will use several pages to introduce how we build the Inkbase. We first select 100 objects from the 18,000. Then we collect humans' interaction with them. We ask the human subject to perform the intent of use, lift up, hold, and also ask two subjects to perform human-to-human handover. We'll cover the intents of give and receive. In order to semi-automatically collect the pose of hand and object during the interaction, we'll set up a visual mocap system to record the interaction of hand and object. We name this mocap system YONGDO, stand for you only need to do once. Then, since we have recorded the hand interaction with only a limited number of real-world objects, for example, one instance of mark on the left, we want to transfer those interactions to the large number of virtual objects within the same category and a similar affordance. The transferred hand interaction should not only ensure its physical plausibility, but also keep the consistent intent and match the size, the shape, and affordance of the target object. We find that the direct post-copying would fail. Hence, we design a hyper-learning fitting method, TINK, for transferring the interaction knowledge. TINK consists of 3 subsequential modules, namely shape interpolation, contact mapping, and post-refinement. Given a source and a target object, we want to transfer the hand interaction from the source to the target object. An instant question is how to express the object shape and perform continuously shape deformation. We represent the object shape as an implicit function, SDF. Now, the question becomes how to perform the shape interpolation between two object SDFs. We train a neural SDF model, Deep SDF, that maps a complex 3D shape into a continuous latent space. Hence, we can perform accurate shape interpolation in the latent space. Next, we need to find a piece of consistent information shared among the source, the target, and all the interpolated objects along the path. Compared to pose, contact regions are more invariant against shape deformation. Hence, we map in the per-finger contact region from the source object, subsequently pass through the interpolation landmarks, and finally reach the target. As long as the interpolation intervals is small enough, we can neglect the shape variance between two consecutive landmarks. Finally, we use the contact and kinematic constraint to optimize the grasp on the target object. Here, we show some transferred interactions after tink. All the recorded interaction in the Yangzhou system and all the transferred interaction after tink fulfill our second knowledge base, Inkbase. We provide cross-data validation of OakInk image subset and quality assessment of OakInk shape subset. We benchmark the OakInk dataset on hand-matched recovery, hand-object pose estimation, and grasp generation task. We show some qualitative results here. Thanks for your listening.